Welcome back, learners. In the previous class, we were discussing about the properties that we are going to define, right? Like, for example, when I go to the define, so we have discussed about the material properties in detail. So after the material property, then when we move to the section properties, you can see that in the section properties that you have the frame sections, then you have tendon sections, then the slab sections, then deck sections, wall sections. So these sections we have come across in detail. Okay, so after that you have four more properties, right? You can see that reinforcing bar sizes, link or the support properties, then frame bar wall non-linear hinges, then panel zone. Now I'm not going to explain that in detail, because as you know that these four properties will be useful so when we go to the higher level of the designs, but you should be in a position to understand what is the meaning of these properties, right? Where it will be useful, because we are going to solve them. So that's why in that first, if I choose reinforcing bar sizes, okay, so when I choose that, you can see that from the bar, right, till they have given some names, they have given bar ID. Okay, so it means it is a bar of 2 inch diameter. Okay, so the corresponding area they have given, so bar ID they have given number 2, so the corresponding bar area is 0.05 inch square, and it means its corresponding bar diameter is 0.25 inches. Okay, so like that, right? So then 3 is nothing but it is an 0.375, that is 0.12. Then next you have number 4 of 0.2, that is of 0.5. so like that you can see from number 2 to number 18. Okay, number 2 to number 18, right? So you have they have given so the various bars, right? So even you have an option whether you want to clear or you want to sort by bar ID or add common bar set, right? So like that US or SI, right? So when I give SI, you can see that we usually go from, right, Indian standards. If I go 2 mm, 3 mm, 4, 5, 7, 8, 9, 10, 11, you can see. So Indian standards we start from 6 mm, 8 mm, 10 mm, so 12 inch, 14 inch, 16 inch, like that they have given up to 50, right? So you can have a set of bars. So where we are going to use this option is in the next coming lecturing videos, we are going to do the design of this, right? So when we do the design of this, we have to define that from where to where your bar diameter has to be designed. Like for example, when I give the software to do the design, right, so there will be a particular column, and on that column a particular dimension has been given. So based on the load coming on that column, based on the moment coming on that column, the software will design the column. So when it is designing, how it will start designing is, it will start from the diameter, that the lowest diameter that it can take as per IS code. Okay, like for example, when it comes to column, we don't go less than diameter of 12 mm. So it will start doing from 12 mm, right? So first it will do the 12, so it will check whether the column will be safe or it will fail. So if it is failing, then it will go to the 14 numbers, right? So then it will do the design according to that, and it will give the number of bars like that. Now when I am doing when the software is doing like that, you have an option to restrict the diameter. That means you don't want any 14 mm bars, right? You want either 16 mm or you want 20 mm or you want the combination of 16 and 20. So then what you can do, you can make a set of bars of only 16 and 20 mm for the column. Okay, so 12 and 16 mm for the beam, and like that only 12 mm for the slab. Like that you can make a group, and when you define and when you assign, when the software is doing the design, it will design the column for the 16 mm. So if not possible, it will go to 20, or if not, it will take the combination of 16 and 20. It won't take any other diameter because you have specified the limits that it has to be 16 and 20. Similarly, call beams also, either it will do for the 12 or 16 or the combination of two. It won't go beyond that. Right? If you have not given any boundary, then it will do as per the IS codes with the minimum diameter. Right? So that is what we call it as reinforcing bar sizes. That is one of the define option that you can see that we are going to use during the design. The next that you can see here is the link or the support properties. Now, this link or the support properties, that what you are going to see, it is definitely of the higher level. Okay, so like especially we are going to use this option when you are going to design a particular structure, okay, for the earthquake resistant structures. If you are designing a particular structure for the earthquake resistant, so then usually we are going to use these options, right? If you want to see, then you will come to know that how you can use it, right? You can see here, you can give the property name, whatever the name you want, and you can give any notes if you want. Now you can see here what type of link that you want. You can see first is damper. Okay, you have an option called damper, right? So dampers is one of the structural component that you are going to use in the buildings in order to absorb the energy, okay. Especially they are used in the earthquake resistant structures, or they are used in the very tall buildings in order to avoid the vibrations developed during the earthquake or during the wind blow. Like when a very tall structures are present, due to the very high wind velocity, so there will be a development of vibrations or the lateral forces in the structure. So now there should be some instrument in order to minimize those vibrations, and it has to effectively make the structure stable during the wind or the earthquake. Similarly, when the earthquake happens, you know the earthquake waves propagate in the soil, right? So when they propagate in the soil, since our buildings are in contact with the soil, so whenever the earthquake moves in the soil, so the waves will be transmitted from the soil to the building. So that's the reason the building will start vibrating. Now, if you have some instrument or if you have some phenomenon to absorb those vibrations, then you can safeguard the structure to some extent, so that you can save the life of the people to a very good extent. And nowadays, due to the very good technologies available all over the country, so many countries are hugely working on the earthquake resistance buildings, especially if you go to Japan, so where an earthquake is a frequent phenomenon for them. They have a very good advanced technology in building the earthquake resistant structures, right? So in that you can see that these dampers, what they will do, they will absorb those energy, okay. So by absorbing those energy, so it will make the structure stable, right? So that is what you call it as dampers, right? So in that you can see that you have three option dampers here: exponential, bilinear, friction spring. Now to this level, if I start explaining, it is very difficult for you to understand. In general, I can say that damper, exponential, bilinear, friction spring means there is an behavior nature of the dampers, okay. So based on what type of building it is and based on what type of vibration you want to mitigate, the behavior of the dampers will be decided, and then it will be chosen accordingly. Exponential means, as you know, so if something increases, another component also will increase. That is what you call it as exponential. So like that, bilinear, friction and exponential, these are the three different ways of the behavior of the damper. So based on its usage, so you are going to use that. Okay, even this gap or hook or multilinear elastic, all these are also some of the other types of links that you are going to use. Then you can see here rubber isolator, friction isolator, T-bar C friction isolator, triple pendulum isolators. So again, these are one of the most effective way of the instruments or the components that you can use in the buildings to protect them from the earthquakes. So what these isolators do is, so they deviate the earthquake waves which comes in the soil. So by deviating them, it will not make the earthquakes to transmit into the buildings. It will avoid it. Either it will absorb or it will deviate. Therefore, whatever the energy which is transmitted in the soil through the waves through the soil will not be transferred to the buildings. So therefore, the building will be safeguarded. Okay, by that way you can use this. Okay, so therefore if I choose that, so it will ask you the different, it will ask you, if I use damper exponential, it will ask you what is its mass, weight. Then rotational inertia, that means inertia in one direction. That is, if I open, if I see, if I want to understand this, so I'm supposed to study the manual of this software. In that they will tell you what is this rotational inertia of that particular exponential damper means. So you should be knowing that value. You should be knowing rotational inertia in the second direction, third. Okay, and you can see the directional properties also. You have u1, u2, u3. That means the degree of freedom, what we call. Usually when I take any of these link, whether it is a damper or a hook gap or multilinear elastic, plastic or plastic ven or isolator, you will be having 6 degrees of freedom. That means translational effect along x, translational effect along y, and translational effect along z, as well as rotational effect along x, rotational effect along y, rotational effect along z. All these 6 degrees of freedom will be present. Okay, so all these 6 degrees of freedom will be present. For example, if I want to say, I don't want to go it in deep detail, but I'll just explain you. You should know, understand, or you should understand what do you mean by that. If I want to write it in 3D, so this is one direction. Okay, so this is another direction. And you can see this is another direction, right? This will be x, this will be y, this will be z. So therefore I can have the transitional effect along x, the transitional effect along y, the transitional effect along z. Similarly, I will be having the rotational effect along x, okay, the rotational effect along y, as well as, okay, the rotational effect along z. Right, now you have an option here whether u1 represents one direction, u2 represents another direction, u3 represents another direction, that is transitional effects. Similarly, r1, r2, r3 represents rotational effect. Now you have an option that you can define the damper or the gap, hook or plastic elastic or ven or isolators in such a way that you can make all 6 degrees of freedom to be working, or you can make any 3 degrees of freedom or any other 3 degrees or any other combination. Like if I choose now fix all, means all the degrees of freedoms are restricted. There will not be any transitional effect along 1, 2, 3 as well as rotational effect along 1, 2, 3. Right. So if you want only this, you can choose direction u1, you can make it either fixed. If I fixed it, so then no need to change property. If I'm not fixing, then you are supposed to give the effective stiffness, effective damping along that. Okay, or if you go to U2, then again you want to choose whether effective stiffness, effective damping. Again in that option you can choose whether you want linear or you want non-linear. If you are using non-linear, then you are supposed to give how it's going to vary, non-linear properties, stiffness, damping, damping exponent, everything. So like that, for each and everything you have an option, right? So if I choose isolators, so there again you have different properties. You can see I can choose this, so stiffness or damping. So if I am making it as okay, so if I am making it as now, see here, so that is effective stiffness or damping, right? Friction isolator, rubber isolator. So like that, so many options are there. If I am making as now non-linear, okay, if I am making as non-linear, so like that, so you can define all these types of link properties, and they are applicable either at the foundation level or at the buildings. Okay, they are used either at the foundation level or in the middle of the buildings, right? Anywhere we can use this. So that is about another important defined property, what we call it as the link support property. The next you have is the frame or wall non-linear hinges. So this again it is one of the property that we are going to use it, especially when we are going to do an analysis called as we call that analysis as pushover analysis. Okay, in order to understand the behavior of the building along the lateral loads. Okay, the lateral loads may be the wind load, or the lateral loads may be the earthquake load. So how the behavior of the structure will be when a building or a structure is subjected to the lateral loads. So in order to clearly understand that concept, so you should do an analysis, what we call it as the pushover analysis. When I am doing that pushover analysis, that time we need this frame or wall hinge properties. Okay, so you can see if I choose the steel means, so you can see that force controlled or the deformation controlled, like that, in which direction you want, whether axial load you want, shear in one direction and shear in another, whether torsion or moment. Then if you want any interaction, that is moment interaction about M2 and M3, or moment interaction with M2 and P, that is moment and axial load of one direction, then one more moment and axial load of another direction, then you have one more moment along two directions as well as axial load, right? So like that, you have different combinations. You can choose any of these and you can define it. Okay, so that property, what we are going to call them as this frame or wall hinge properties. Okay, so frame or wall hinge properties, right? So then the one more option that what you can have here is the panel zone. So that is also, you can see that depends upon when you have a special design of the structures under the lateral forces, that is wind and earthquake. Okay, yes, so that is all about this. So for this particular problem, understanding the section properties of the frame, tendon, slab, deck and wall is more than sufficient. So this reinforcing bar sizes we will be understanding thoroughly when we are doing the concept of design, and this link support property, this frame, wall, non-linear hinges and panel zones will be doing when it comes to the lateral loads on the structure, that is wind and earthquake. Okay, now the next that you can have is the spring properties. This entire spring properties is going to deal at the level of foundation. Okay, at the level of foundation. Now again I will tell you, this spring properties, again we are not going to use this concept when we are doing a normal type of design and analysis. But When it comes to a special type of design, what we call it as a soil structure interaction. So you may have the doubt that what do you mean by this soil structure interaction means. See, to be frank learners, you know any structure will be resting on the soil, correct? You cannot have soil separate, you cannot have the structure separately. Every structure has to rest on the soil, right? So when we are doing a normal or a simple building design, we can assume that the soil is separate, the building is separate, and that is what we are going to assume also practically, that there is no any interaction or the relation between the soil as well as the structure. No, we assume that the soil behaves in its own way separately, the building behave in its own way separately. By assuming that, without considering anything about the soil properties or its nature, we consider only the building and we analyze it building ideally and we design it and we'll do it. Okay, for normal kind of problems, for a very simple buildings, it is sufficient. But when you go for a very huge structures like bridges, which cost crores and crores of project, bridges, dams, okay, and especially a very huge buildings which are present in the earthquake zones areas or earthquake resistant structures, there you cannot consider the structure separately and the soil separately. There will be an always interaction of the building and soil together. That is what we call it as soil structure interaction. The properties of the soil will have effect on the building, right? So that's why we cannot neglect the presence of soil and we cannot consider only the presence of building. Both effects has to be considered in the design. That when we consider the effect of soil on the building, definitely your design approach of the buildings is completely different. Okay, so you have to be more conservative in nature. You have to consider the properties of the soil also. By considering that, you are supposed to design it. So that time in the software, when you want to have that effect, that is soil structure interaction effect, we are going to model the soil in the form of springs. Okay, because we cannot put soil here or we cannot consider soil below the foundation. That's why at the foundation, after the foundation, we define the springs and that springs behave as an soil. Okay, that springs behave as an soil, right? So in that, when I see point springs means we are going to consider that the soil is present exactly below the foundation. So I'm going to consider a particular area about that particular footing, then I'll consider soil structure interaction, then I'll do the design. So that time I don't bother about other columns as well as the area of the soil surrounding. No, which column I have considered, only that column surrounding soil I'll consider and I'll do. That time we are going to use the point spring options. Okay, you can see when I choose point spring means again we are supposed to define these values to that. That is, what about the transitional stiffness that you can give in X, Y, Z, as well as the rotational stiffness in X, Y, Z. Okay, so you, and again this link properties, everything you will add it. Okay, so everything you will add and you can give the direction also, in which direction you want, everything, angle, everything you will give. Okay, so that is with respect to point. I told you, we will consider only at that point and we will do. That is point springs. Now in case if I want for a very lengthy area, for a long distance, then we choose line springs. Okay, so when I choose line springs, so then it will be for a little longer length. Okay, not about a particular point, over a period of over a length or a distance. Okay, so when you have an over a length, then immediately it will come that whether it is linear or you want it non-linear, because you know the soil is a very peculiar one where its property is going to change in all directions from point to point. Okay, so therefore you will be having an option to choose whether in the second direction, that is either x or y, third direction means x or y, whether it is linear or it is non-linear. Okay, and even whether you wanted to do for the compression or you wanted to do for the tension, all these options you can choose and you can do it. So when you are doing for a little length area over a very particular length, you go for the line spring property. When you want it over a very huge area, okay, when you want it over a very huge area, you can go for the area springs. Okay, there also again you have linear, compression, tension. So like that, what it is when we are going to do that time we can express. Okay, so that is about your area spring properties. That is about everything about the spring properties. Okay, so soil profile also you have an option to define. Okay, right, you can see here. So when I am doing that, you should be knowing the soil. Okay, you should be knowing that data. Okay, you should be knowing that, right? Like for example, you can see here soil layer name, you can give one particular. So elevation of the top of the layer, what depth of that soil is there, right? You should be knowing what is the unit weight of that soil, what is the shear modulus, what is the Poisson's ratio, what is cohesion, what is friction angle, what is shear wave velocity, everything, color. So then when I add it one more, like that you can give the soil profiles. Okay, you can use the soil profiles like that, and you can give the names also to that. Okay, you can give the names. So like this, n number of soil layers you can add. Either you can add it in the vertical direction or in the horizontal direction also, both options. That is soil profiles. Okay, so the same thing you have another option here, isolated column footing, you can see. Okay, it is an isolated column, right? So length, isolated column footing, dimension, length along column major axis, width, thickness, everything you can do. And you can footing embedment depth, that means to what depth your footing has been present inside the soil, right? So either the program can detect it or you can give user defined also, right? So like that. So these are the advanced options that you can have, okay, that you are going to use in the spring properties option, right? So the next that you can have is the diaphragm option. Now before we define anything, you should be knowing what is the meaning of the diaphragm or why it is required. You may have a doubt. See, the software will analyze the structure by considering the entire building or a structure as a single one. Okay, so it doesn't want each and every component to be considered separately. It wants everything to come under one particular point only. It wants everything to be under one particular point. Okay, so that is why especially when it comes to analysis of your slabs, okay, so the software has to consider all the slabs together. Otherwise what will happen, so it will affect the results and the designs becomes little complicated. In order to avoid that, so we have an option called a diaphragm. So what it will do, when I apply diaphragm to the structure, the each and every corner of the slab will be held in position at the center of the building. Therefore when I do the analysis, right? Each and every corner will be considered simultaneously and analysis will be done effectively, right? For example, I can choose this entire structure and I can go to assign. Since I have defined the diaphragm here, I can go to assign, and I already told it will be assigned for the slabs joints. So I can go to the shell, and there you can see that you have an option called a diaphragm. So when I click on that and when I give apply, you can see that each and every corner, okay, if I go to plan, it will be very clear to you. You can see from each and every corner of the slab here, okay, everything will be concentrated at the center, what we call it as the center of mass, okay, we call that as the center of mass of the structure. So everything will be concentrated at the center of mass. So this position of the diaphragm will vary depending upon the plan, okay. Since there is an opening, you have an center of mass or the diaphragm center here. So if you have something else, then definitely you will be having the position of the diaphragm some other positions. It depends upon the plan of the structure. This is how it considers each and every corners of the slabs, and it makes entire slabs as a single, and it will analyze. That is what you have an option called a define option in the diaphragm, okay. So then once it is done, so let us see about this peer labels, spindle labels, group definition, section cuts later. The next you have an option called functions. You should understand that what is this functions. Now, whenever you want to analyze any of the particular building, okay, whenever you want to analyze any of the particular building, there are, as per the IS codes, as per IS code standards, there are two ways of analysis. One we call it as the static analysis, another one we call it as dynamic analysis. First we have to understand what do you mean by static analysis and why it is required. What do you mean by dynamic analysis, why it is required. Now, static means it will act on a particular point and it remains same. Static means it is going to remain same over a period of time. Like for example, now I have a building, I'll apply 10 kilonewton load on that particular building or a member, and at 0 time the load acting on that member is 10 kilonewton. At first second or the first time is also 10 kilonewton, second 10, 5, 10, 10, at the 10th second also it is 10, 50th second also it is 10, 100th second also it is 10. So like that, if you consider any of the time, the magnitude as well as the position of that load will not change. It is going to remain stagnant. So that we are going to call it as static. And if I am doing static analysis means, the load whatever we are going to consider on the building or the structure will remain same throughout our analysis and design. It is not going to vary over a period of time. That is what we call it as static analysis. Doing the static analysis is very easier because we assume that the loads on the structure will not change. It is going to remain over a period of time. So that design is very easy. But when your magnitude of the load, okay, when your magnitude of the load is going to vary for each and every duration, okay, like from first minute or for a first second to second, If your magnitude of the load is varying means, then we call them as dynamic. Okay, that is, the load is going to vary for an every duration, every second you can say. It is not going to be constant. Okay, so when you are going to analyze the structure by considering that dynamic load, which is going to vary for every period of time, or it may be, when I say a period of time means it may be a fixed period of time or it may be an irregular one. Okay, so that type of analysis we are going to call them as dynamic analysis. When I take the wind load acting on the structure, okay, right, so sometimes even the wind load will also be a dynamic load, because it may going to vary. Not only wind load, the best example for the dynamic load that I can give is earthquake, because when I am taking earthquake load, it is going to vary for each and every second. Okay? The load applied on the structure at the first second is completely different at the load acting on the structure at the second. Either the magnitude of the load may increase, the magnitude of the load may decrease, the magnitude may be same but the direction may reverse, which may act at left to right at the first second may change to right to left. Anything can happen. That's why the best example for the dynamic loading is earthquake. So, and not only that, your earthquake will act on the particular structure for a particular interval of time. It will not act for an hour, it will act for a seconds, minutes. So that time there will be a very large variations in the load. If you design that particular structure for only one magnitude of the load, then if the magnitude of that load which is acting on the structure at any one particular point in that earthquake, if it is higher than that, then your structure is going to collapse. Okay, so that's why when you are considering earthquake or wind, you have to design in such a way that by considering the dynamic analysis, that means by varying the loads. So when it comes to the dynamic analysis, we usually, that is Indian, we follow two methods. We call them as response spectrum and we call them as time history. Okay, so response spectrum and time history are the two methods that we can follow in the dynamic analysis, right? So what is that? That definitely we will go in detail. So when we are doing the earthquake analysis, but let us now briefly explain what is this response spectrum and time history, right? So this response spectrum or time history, as I already told, they are the two methods by which you can design a structure as a dynamic one. Okay, this response spectrum, what it is going to do is, if I see IS 1893-2002, okay, which is suitable for the earthquake resistance design of the structures, there we will be having the different parameters, what we call it as the importance factor, soil profile, okay, response reduction factor, seismic zone factor. So like this, there are different factors to be considered, right? So in this response spectrum method, we are going to consider that. We assume that our building or our structure, what we are going to design for the dynamic analysis, we assume that it is going to be subjected to earthquake in the future. Okay, so therefore in IS 1893-2002, the India has been classified into the 4 zones, zone 1, zone 2, zone 3, zone 4, based on the frequency or the repetition of the earthquake happened over a period of time. So we have to choose in what zone our building is present. Okay, so zone 1 means it is of least earthquake affected area, 4 means highest affected area, right? So every state, every major cities of the India has been classified into under the different zones. After that, we are supposed to choose what type of soil that you have there, whether you have a hard rock soil, soft soil, or medium soil, because I already told earthquake waves moves in the soil. The nature of soil plays very important role. That also we are supposed to choose. Okay, and not only that, you are choosing the building. No, you should know what is the importance factor of that building. That means you are supposed to know what type of material you are using, what type of building you are using, what is the use of that building. That also plays a very important role, right? So by considering those factors, we can do a dynamic analysis. I'll just show you add new function. Right, before I choose add new function, I am supposed to choose, you can see IS 1893-2002, right? So when I choose that, now all the data, whatever it comes, will be as per that. Okay, you can see here seismic zone factor, what it is, then soil type, what it is, what type of, you have 3 categories of soil. So like that, based on that, you can define the response spectrum function that acts as the dynamic load, and you make it to act on the structure, and you design it for that dynamic load. That is one type, what we call it as the response spectrum. The another one, what you can see here, is called as time history. This is here, what we are going to do is, we will be considering the real happened earthquakes in the past. Okay, we'll be considering the real happened earthquakes in the past, right? So in particular websites all over the world, whatever the earthquakes happened, their recorded data are available, right? Like in India, if you take, you can have a Burj earthquake, right? So like that, whatever the earthquakes happened, like the very famous earthquake, you can have Kobe earthquake in the Japan, okay, or Chichi earthquake. So like that, some Atlanta earthquake. So like that, some all the previously recorded earthquake data will be available. You can download them, and then that loadings will be applied on our structure. Okay, so that loading will be applied on the structure. So by applying that loading, we will make it, and definitely, since you know that earthquake load is a dynamic load, so the building will be subjected to that dynamic loading, and for that loading we are going to design it. Okay, so that is another way. Okay, that is another way of doing the time history. As the name itself indicates, the time history means it is going to vary with respect to time. So that is another way of doing the dynamic loading. So response spectrum and the time history are the two methods of doing the dynamic analysis. Definitely, when you are, as I already told, the big projects like buildings, buildings, very huge buildings with high importance in that, or bridges connecting the very huge distances, whether it may be a vehicular bridge or the railway bridges, large dams, okay, large dams. So when you have a very high significance of those structures, definitely we cannot do for just a static loading, we have to do for the dynamic loading. And along with that, definitely we have to consider the soil as well as the building together, and we are supposed to do soil structure interaction design. And not only that, students, for your information, I'll just tell you, when you are building a particular dam, the dam will be having interaction not only with the soil, even it will be having interaction with the water also. right? That's why there is another advanced level also, what we call it as, along with the soil structure interaction, there will be liquid structure interaction, because the dam has to have the interaction with the liquid also, that is the water which is going to be stored. A very huge amount of pressure will be pressure will be acting on the dam. So therefore there you are supposed to consider the soil structure interaction also, the water structure liquid structure interaction also. Not only in dams, if you have a very huge elevated water tanks, there also you'll be having the liquid inside that, as well as it is resting on the soil, where both soil structure interaction and liquid structure interaction will come into picture. Okay, definitely it is an advanced level, so no need to worry much. For your information, I just told, right? So therefore we have seen all these things. So let us stop here, and in the next video let us see about the generalized displacement Marceau speed delta option model case with respect to loads we will see, and then we will start the analysis already we have done. We'll start the design of the beams. Okay. Thank you, learners. Thank you so much.